Thank you very much, Martin. I'd like to thank the organizers for inviting me here. So this is a conference where Sigmod Pods is something that I've followed from afar. So I'm very glad to have the excuse to come down here and actually attend the conference. I've got one. Thank you. Yeah. So this is the title of the talk: in-memory representations of databases via succinct data structures. And so that's sort of the outline of the talk. First, there's going to be a little bit of an introduction, and then I'm going to sort of beat some data structures at you, and then just a little bit about what libraries there are. Raise a little bit. Yeah. Oh, they wrapped it around a few times. Okay. There's some kind of quote about premature optimization being the root of all something or the other problems. So somebody's actually now, okay, there we go. Yeah, all problems. Yeah, that's good. Brilliant. Yeah. So is that better? Okay, great. Yeah. So like I said, so that's basically going to be the structure of the talk isn't very obvious over here, but if you can read the grayed out font over there, then I'm basically going to talk very briefly about libraries that you can use for succinct data structures, and finally I'll come to applications where these are basically applications in databases and data management. Yeah. So this is the content of the talk, and the content of the talk is basically an introduction to succinct data structures. Now, the thing is that there are thousands of papers now on this area. For any kind of data structuring problems, there are many data structures available. If I were to try to cover even one of these data structures in detail, it would take me 3 hours. So I don't intend to do that. So what I'm going to be talking about are from fairly simple data structures. These data structures may not asymptotically be the best. So if you're looking for the absolute best complexity bounds, do ask me questions about this. And what I want to do is I want to introduce you to their strengths. Succinct data structures have lots of strengths, but they also have lots of weaknesses. So it's definitely not any kind of magic bullet out here. And like I said, I'm going to give some examples of uses of succinct data structures in some database applications. So like I said, this talk is not going to be anything like comprehensive. So after this talk, you're not going to know all about succinct data structures. For this, I would recommend a nice new book that's come out called Compact Data Structures, A Practical Approach by Gonzalo Navarro. And then there are a number of articles online, and I suggest to you particularly try to read the articles by non-theory people, because non-theory people just get straight to the point and tell you what you need to know, and not this. And so particularly, for example, I found one of the authors of yesterday's best paper is Dave Anderson, and he writes little blog posts and little articles about these. I actually find them easier to read than my own community's articles. And then there's going to be hopefully a monograph by myself and Simon Polisi on this subject. We should hopefully have it ready for early next year. And there are various survey articles, but these survey articles are then again written focusing on one of the succinct data structuring problems and just beating them to death. And the question is how interesting these are for the non-theory community. And of course, the next thing is to find a researcher in succinct data structures and go and talk to them. This is usually the recommended option. And I think most people are very willing to consider applications in this field. Okay, so what's the aim of the talk? The title of the talk was a bit of a lie. I said there are in-memory databases based upon succinct data structures. There really aren't any. There are some kind of half-baked prototypes and proofs of concept. And so the aim of this talk would be really to make the title of this talk happen. So it would be really nice to have a reasonably fully fledged database system built upon succinct data structures. That's very far away. I'm not really expecting that to happen in next year or so. Okay, so first of all, I want to sort of tell you what the point of succinct data structures is. And this is sort of the what I hope is the selling point. So you've got there used to be a reference on this slide and it got lost. This is basically from a talk in KDD. These two terms are from a talk in KDD 2013 by John Canny. And the point is that there's big data and there's big data. So this is capital B and this is lowercase b. And the claim is that a lot of data that we are dealing with is actually lowercase big data. And this is like tens of hundreds of gigabytes. So these aren't, it's not enormous data sets, but large enough that if you process them the wrong way, then you're going to get into trouble. So the point, of course, is if you read a lot of papers in this community, data mining community, they will sort of talk about you're trying the really sort of throwing very heavy machinery at it, like, lots of optimizations for disk accesses, distributed processing, streaming, all this kind of stuff. But the data sets they're using are typically more in this category. So, and if you're trying to work in these kinds of modes, then you're basically handicapping yourself. Many simple tasks become very hard or impossible. So theoretically, for example, it's very hard to do a breadth first search on a graph in external memory. So therefore, the claim is that if you could just have in-memory databases, then lots of things become a lot simpler. So why don't we all have in-memory databases? And the problem is really that most of the time we've got data. The data might not be very big, but we want to obviously want to ask queries of this data. To ask queries on this data, well, then you have to have an index on the data, and the more complicated your queries, the more complicated the index. And quite often it turns out that the index becomes much larger than the data. So a couple of examples from the theory community. There's two data structures called range trees. So range trees are basically KD trees with theoretical guarantees. So they actually run in worst case log n time for answering orthogonal range reporting queries. The only problem is that they take n log n words of space. So if you've got so typically you take a theory book and something you say takes order of n space, well, this one takes order of n log n space. If you've got relatively large data, you definitely don't want order n log n space. The problem could be the constant. It could be the log n. The fact is we really want data structures. Our selling point is we want data structures where the data structures, including the index, is actually not much bigger than the data that you have. So, yeah. So both of these are issues. But in this particular case, the constant isn't terrible. But yeah. So yes, then you got this other data structure called suffix trees, and suffix trees are all singing, all dancing, pattern searching data structures, and they answer all sorts of amazing queries on. There's actually a paper called The Myriad Virtues of Suffix Trees, which lists about 30 or 40 things that you can do with suffix trees. It's really very nice. But the thing is that a suffix tree also looks quite nice, because if you have a suffix tree on a sequence of symbols of length n, that takes order of n words of space. So it's linear space, so people are happy. But unfortunately, this is another thing when it comes to relatively large data sets. So when you say a word, so if you've got an input of size n, then a single machine word had better be at least log n bits long. Otherwise, you can't even store the integer n inside it. You can't address an array containing n items. So therefore, one word must have at least log base 2 of n bits. So therefore, n words is basically omega of n log n bits. But the raw sequence is n log sigma bits, and sigma is the size of the alphabet. So if you're thinking of, for example, sigma being the genetic alphabet, then this is 2. And in practice, this log base 2 of n is 64. And so you can see where the problem arises. So a good implementation of suffix trees where people try very hard to reduce the memory usage and so on can be 10 times to 30 times more space than the raw text. And this is not very good if you've got quite large data sets. Okay, so this is the basically the motivation for this area. So what happens is that we say that, okay, you've got two things. You've got the data, so you've got a data structure. Presumably it needs to hold on to the data. So the overall space usage should be the space for the data plus the space for the index. And the space for the index is considered to be extra, and that's the redundancy. And what we really want is that the redundancy should be of a smaller order than this space for the data. Okay? And of course, the thing is you can do this by cheating. what you could do is you could sort of somehow store the data in a compressed format. Then every time you have to answer a query, you read it off the data and then build a huge in-memory data structure and say, oh, this isn't really this is just my temporary working space. You shouldn't count it. Obviously, that kind of stuff is not something that we want. So we basically want small working space as well. So one of the things that we want to first thing I want to talk about is, what should be you say the space for the data plus the space for the index. The question is, what should be the space for the data? And this is, again, something which we need to look at a little bit carefully. So this is it's a fairly obvious way of measuring the space that you need for your data. And it's not the size of the file that you got or something. It's a little bit more theoretically well-founded. And this is it's a very obvious information theoretic lower bound. And this word appears all the time. So I'll be abbreviating it as ITLB, which is a horrible abbreviation, but that's fine. So the idea is very simple. If you've got an object X, and you know that this object comes from a set S, then the minimum number of bits in the worst case that you need to represent X is basically log base 2 of S bits. Okay, so that's obvious. So let's put this into practice. So first is, our object is a binary string of length n. So it's got n bits. So what's the size of the set? Well, the size of the set is 2 to the n. I took log base 2 of 2 to the n. I get back n. It's kind of boring. So basically what I'm saying is the information theoretic lower bound for storing n bits is n bits. Okay, so it's kind of, it's true. Sometimes there's nothing to do. So now you can do a little bit slightly better. So what happens if you say something else? That this is a bit string, but you have relatively few m's. So just ignore this n over 2. That's really you don't need that for now. But you've got a binary string of length n with just m1 bits. Okay, so when you think about this, then if it's a binary string with just 1 bit, then you can encode this binary string by saying where that 1 bit is, and that's a lot less than n bits. Yeah? But in general, you can do this. So what happens is you can sort of look at this as it's a binary string of length n with m1 bits. Well, there are n choose m of those things, and so that's the size of my set S. So my information theoretic lower bound is the log base 2 of the size of the set, which gives you this over here. So it's kind of a ugly looking expression. If you work in succinct data structures, you will learn to love it. It's actually quite a very useful little expression. And what this means, for example, is that if m just happens to be if your bit vector is not too dense, right? So something like it's somewhat less than n, then this actually gives you a fair amount of savings. So for example, in a theoretical way, if you sort of took m to be n over log n, then you basically use m times log n bits, and that's if you just multiply this over here, then you get little of n bits. So under this circumstance, you actually have a information theoretic lower bound that's less than the raw representation of the data. Binary trees, well, if you know that your object is a binary tree with n nodes, S is the set of all binary trees of n nodes. This is the number of trees there are, and you take the log base of this, then you get basically 2n minus order of log n bits. So that's the information theoretic lower bound for storing a binary tree with n nodes. You can see where the attraction is. If you take a binary tree, how would you normally represent it? You would say here's a node, and there's a pointer to the left child, pointer to the right child. You might actually perhaps even want a pointer to your parent, and that's 3 pointers. 3 pointers is, if you take a pointer to be 64 bits, it's 192 bits, and here I'm promising you a tree with just 2 bits per node. So there's a big saving over there. So this is an example of where succinct data structures can save you a lot of space. And here's some other stuff. So graphs are usually incompressible, but certain categories of graphs, certain classes of graphs have got behave more nicely. So for example, if you've got triangulated planar graphs, then rather than just storing the graph in its raw format, then you just take the information theoretic lower bound, and it's basically just over 3 bits per node for representing a graph. So that's the information theoretic lower bound. So what we actually want is, one thing I want to say is that this sounds a bit like data compression, but it's actually not. So succinctness is not the same as compression at all. For example, the information theoretic lower bound doesn't care about the actual instance you have. It just says if I have a bit string of length n. But if I gave you a bit string of length n, and this bit string just happened to be very nice. It was, lots of zeros followed by lots of 1. Well, the information theoretic lower bound says these are the same. So then we have this other area called compressed data structures, which then look at the compressibility of the data, and this then becomes another sort of huge little sub area over here. And the aim, which you'll quite often see, is something called, you'll see this term called HK. HK shows up all the time in compressed data structures. So what is HK of S? So we'll just, the kth order, this is called the kth order empirical entropy. This is best defined for a string. If you have a graph, then for all these things, the higher order empirical entropy is not very well defined, so I'm not going to try to define it here. So this is the kth order empirical entropy of a string S, and this basically says that if I knew the previous k bits of the string, how well can I predict the next bit of the string? So over here, if I know one previous bit, then I can actually do a really great job of predicting the bits in this string, because all the time I just predict the bit to be the same as the previous one. Once out of n, I get it wrong, and it's not terribly hard to see that the first order empirical entropy of this string is just log n bits. So if you've got a highly compressible string, the kth order empirical entropy is going to be much smaller than the raw representation of the string. And this kth order is basically, for example, if you compress a string by bzip or by a nice compressor, then all of these things asymptotically will achieve the kth order empirical entropy. And so there's quite a lot of work over here which says that rather than just try for the information theoretic lower bound, let's try for storing the data itself in its kth order empirical entropy space and then perform operations on it. Then that's fine, and then there's another sub area which is now growing quite rapidly because this kth order empirical entropy doesn't sort of handle things like genomic sequences where, for example, if you want to store one genomic sequence, yes, kth order empirical entropy is useful, but if you want to store 100,000 genomes, all of which are very similar, then this doesn't capture that kind of similarity. So you have quite a few people who work on things called grammar compressed strings. What's grammar compressed strings? It means that you think of some kind of compressor which magically comes out with a straight line program, and when you run the straight line program, the output is basically the string that you were trying to compress. So the size of the straight line program is the size of the compressed string. So this is the space for the data, and now what you want to do is you want to do operations on the data when it is compressed in this particular form. This stuff I'm just not going to go. I'm just telling you that it exists. So if your data is highly compressible, then it's worth looking at this side of the literature. Okay, good. So this is the so we're now going back just to plain succinct data structures, not looking at the compressibility of the data that much. And so the aim of the succinct data structure is the space usage should be basically broken up into two components. One is the information theoretic lower bound for the data, and then the space for the index. And what we want the space for this index should be a lower order term. So asymptotically, it should be growing slower than the space, the information theoretic lower bound. And obviously, what you want to do is to perform operations directly on it. Okay, so this is the theory part, and then the practical part is you've reduced the memory usage typically by an order of magnitude, and this is the expense. Of course, you have to. It's a little bit more complicated. You may have to do a little bit more processing to get the answers. But the thing is that what happens is because you make better use of things like cache and TLB, you reduce your processor memory bandwidth. And then, so therefore, SDSs are typically speed competitive with normal data structures. So if you've got a normal data structure and the data isn't so big that the normal data structure doesn't fit in memory, then the SDS will be maybe a couple of times slower, perhaps, unless you're very good at engineering this SDS. But obviously, the main point is that you can handle larger data sets. And also it turns out that if you're using multi-core settings, then you've got multi-core shared memory and stuff, then again, reducing the amount of memory communication is very good. And there's a paper by Julian Shun in DCC 15, where they basically report that by storing the graphs in some kind of compressed format, they actually managed to get better speed-ups for many graph algorithms. Okay, and the really nice thing which I like about this is that if you take a SDS and you say, well, here's my data, here are the operations I want to support on it. And if these set of operations happen to be exactly the same as the set of operations that you want from a normal data structure, then the data structure then becomes a separate part, and you can take the SDS and you can plug it into a larger application, and so that means that if you play the game right, then the SDS doesn't have to be the center of the data structure, but it can be one part, and it can help you for certain things, and so on and so forth, and that would be very nice. Okay, so that's sort of the end of the introduction. So like I said, the aim of this is to take your data. Oh, sorry, I should probably say this last point. This last point is actually one of the things that you really must, this is a very important take-home message, because I was there at best paper talk, and then there was a question afterwards is, so your filter can handle this, can it handle something else? And the answer is it's probably not, because the representation that you have is usually quite tightly tied to the operations that you want to perform on it. And this is something that we'll see. This is typical for us theory people. You pick a problem formulation and then optimize the hell out of it, right? So that's basically what theoreticians tend to do. So yeah, so this is one of the disadvantages, and this is something that we'll see over and over again. And so keep that in mind. ADT, I don't know what to call it. It's just the interface that you want. So it's some people want to call it ADT, abstract data type, and some people want to call it API, and some people want to call it data structure, which really makes me unhappy. But okay, so that's just the overview. So now what I'm going to do is I'm going to actually introduce some concrete data structures. Go ahead, yeah. Yeah.
But here I'm not convinced that this is the right analysis at all. More we could say I have a memory of a certain size.
Yeah.
What size of data can I handle? I would go backwards. If I have a memory of size M, let's say big M, what is the biggest size of data that I would be able to handle when you do this total cost of ownership analysis in some sense? That to me is the right way to look at it, not the big M, because ultimately that's what I want to know. I have 100 gig memory.
Yeah. So theoretically, I mean, so one of the things is, at least in this area, we don't hide behind the big O for the space usage. So in principle, I should be able to tell you exactly the answer to your question exactly, and the same formula applies to you who has 100 gig of memory, and to someone else who has 20 gig of memory. So you should, in theory, so there's no big O's in the space usage most of the time. I hope that sort of, but I think it's a fair point. I mean, it's
there's one constant matter, right, between the size of the memory that I have,
yeah,
and the size of data that
I think it's a people don't do it, but it's certainly something that we should consider. Thank you for that. Yeah. Okay, good. So. Yeah, by the way, so I don't always look at the audience. So if you have a question, just say a question or something, and yeah. Okay, so now we talk about some concrete data structures. So this part, let's see how time goes. I might or might not be able to explain all of them in the full detail. It doesn't look like very many slides, but they might need some work. Okay, so data structure number one. So this is the how do you call it? This is really the very first data. If anyone teaches succinct data, this is the very first thing that you have to know. So it's a very simple data structure, fortunately. So yeah, so you've got a sequence of n bits, x1 to xn, and information theoretic lower bound we know is n bits, so we want to achieve n plus something. So we'll come to that in a second. But let's look at the operations. The operations are extremely straightforward. The first one is called rank of I. So rank 1 over here of I. And rank 1 of I counts the number of 1s in x1 to xi. So you've got rank 1 of 4 over here is there are 2 1s in the first 4 positions, so that's equal to 2. So it's just basically a prefix sum operation. And select 1 is basically the position of the ith one. So for example, select 0 of 4. Well, that's select 1. And then you also have similarly rank 0 and select 0, which select 0 tells you the position of the ith 0. And for example, select 0 of 4 is 7 because the fourth 0 appears in the 7th position of this bit string. So it's very straightforward. These operations, people realize that they're very important. So there's even Peter Ellis's JSEM paper sort of realized this. And then there are a couple of papers by Tarjan and Yao. And then Chazelle did some very nice work on this area. And then there was this guy called Jacobson, who unfortunately who doesn't seem to be in the theory community anymore. And it's very interesting. He got his PhD from CMU, and he wrote the very first thesis on succinct data structures. And it was amazing. And this was in 1989. And then 15 years later, everybody wants to read his thesis, and it's and
What's his first name?
Guy Jacobson. Yeah. So it's. The only thing about him is that he sort of chose the wrong model in one sense. He sort of had a model where he was looking at operating on bits at a time, and that's not very fashionable these days. So perhaps we don't use his results as such very much. But it's a very nice. I actually even went to this particular conference, and I looked at it and I said, interesting. It's maybe not really for me. And then 15 years later, I was reading his thesis from beginning to end. Yeah, good. That's theory for you. So, okay, good. So, and what's interesting is actually this seems to have infected CMU. So CMU seems to contain people, all sorts of people doing systems, programming languages, databases who have absorbed this thesis. And anyway, good. So here's the machine model, and this is where Jacobson did something which is slightly different. And this is the machine model that we work with. It's called the unit cost RAM model. So the RAM model is a straight thing. Basically, it just says that you take a normal programming language, and you take the number of instructions, and each instruction costs a constant amount of time. One thing that we say is that you've got, for example, in an instruction, you can say add 2 numbers. And the question is, how big should these numbers be? And we obviously don't want you to be able to add, numbers with billions of bits together. So we restrict the word size to be log n bits. So but any operation on a log n sized, many operations on log n sized words are basically considered to be acceptable. All of these happen in constant time. This is actually quite a terrible machine model because it assumes constant cost for memory accesses, but let's not go down there. So in this model, in the theory, basically we want to support these operations in constant time and use space of n plus little o of n bits. So that's the name of the game now. This is very straightforward. I'll just try to show you how this works. So this is bit vectors. We want to implement rank. And remember, what is rank? I give you a position. You have to tell me how many ones there are up to the start of this, from the start of the bit vector up to this position. So the naive solution is to basically, okay, you want to count the number of ones. Let me actually write down the number of ones. So for the ith position, I just write down how many ones there are from the beginning. This is not very good because this requires n log n bits, because each of these numbers requires potentially log n bits to write down. So. And if you did this on a real computer, you got a bit vector of n bits, and your rank counts are 64 n bits, and that's a bad usage of space. So what do we do about this? Very straightforward. Well, it's very straightforward. So what we don't do is we don't store every sum. Okay, we just say we choose this in the theory papers. You will see this log n divided by 2. Sometimes you see log n divided by 24. It's all the same thing. A meaningless number in practice. And so, for example, in this example, let's assume that log n divided by 2 happens to be 8. Okay? Then what we do is we just store the sum of the number of ones up to every 8th position. So this is called sampling. Okay, so and this obviously reduces the space usage because these are log n bits, and now you're storing only n over log n of these sums. So therefore, you've reduced the space usage from order of n log n to order of n. Okay, so there is a cost, of course. So if I ask you for a rank query, and the rank query falls right on this one of these sampled values, life is great, you have the answer. But what happens if it falls in the middle over here? Well, you've got these bits to look through. Are you going to scan through them? But if you scan through them one by one, that makes your query time log n, which is not very nice. So, so question, how do you support rank in constant time? And this is how you would do it in theory. So this is how you do it in theory. So this is a trick called the 4 regressions trick, and it's used a lot in the theory of succinct data structures. So, so the idea is this is why we chose log n over 2. So we're going to create a table. Oops, sorry, there's a space over here.
The word size.
The word size is log n.
So isn't every such log n bit 1 word?
Yeah, but then so that's the thing. I lied. I said you could do every operation but now you want to say, so yeah, some in the RAM, in the formal RAM model, some operations are allowed, some are not, and I'm claiming it doesn't really matter because of the 4 regressions trick. It's all allowed. So let's yeah. But that yeah, this is basically bridging the difference between the truth and the lie that I told earlier. Yeah. So basically what we do is we just create a table. So what's this table? This table basically takes a block like this and basically pre-computes all the answers for all such possible blocks. But because the size of this block is quite small, the number of such possible blocks is actually quite small as well. So in the pre-processing stage, before you start answering queries, create this particular table. So this table is going to contain something like there's a 2 plus log k, 2 raised to the k plus log k entries. What are these entries? So the entries basically say the following. You take a bit string of length k plus log k, and this tells you the number of ones in any prefix of this particular bit string. So for example, let's look at this, forget about this, just look at the example. So here's a block. I want to find out the rank up to position 5. So 5 in binary is this, and this is the actual block. So I read the block, I take the binary 5, I concatenate them together, take this becomes an index into a table, I go and take a look at the index, and this actually contains the answer. And this particular value in this particular table should be actually equal to 3 because there are 3 ones in the first 5 positions of this block. Okay, so this is a straightforward trick. This is sort of pretty much sort of the standard method for most theoretical succinct data structures. You decompose your problems. That might take some work. Sample, figure out exactly how to do the sampling for more complicated things, and then you start doing table lookup. So table lookup basically means that for very small things, you just do it in constant time. Yeah.
You need some time to change this to string to access the table in constant time, no?
Oh, these are all log n sized integers, so I can shift one, and so I can do like a.
You shift one of the others, but then you have to OR them.
Yeah, OR them, but OR between log. So these are those basic operations are allowed. Doing prefix sums inside a word is at the moment not allowed in the pure model, or doing a select inside a word is also not. So, but yeah. So this is a theoretical thing, and if you try to do this you try to write code based on this code is going to be slow. Practical implementations, this is it's been going on for the last 10, 15 years. And you have to understand your hardware. You have to understand what instructions there are. Make use of, for example, this stuff can be done using a hardware instruction called pop count. You have to understand how the operating system works, how memory works, take into account application-specific constraints. And for example, unfortunately, in the talk yesterday, the authors unfortunately didn't manage to talk about all these wonderful things. So this really was one of the interesting contributions of their paper for me. But all of this does require a fair amount of work. You can't just take a theoretical. Yeah.
Do this much for levels?
Yeah. Well, so that was your. You just, thank you, you just done your exercise. So this is, you do it multiple levels and you get n plus little o of n. So you break it up and then you break up your logs. Yeah, so it's not hard. Yeah, and then select one is slightly more complicated, but that's also quite easy. Yeah. 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 Right, so I didn't say what x was. So x is, I didn't tell you what x was, so this is a bit of a cheat over here. But x is basically this position over here. So to get to this position, to find out, so there's bit vector starting all the way from there, and x is over here. And so the way I get the rank at this position is to take the 657, which is the sum of all the ones up to there, up to the start of this block. No, that's right, yeah. So yeah, this is the actual sum, yeah. Sorry, it's not a very, yeah, okay. Thank you for that, yeah. Okay, so that's how you do rank and basically how you do every succinct data structure. Though if you take a look at the paper, you might not see this, but basically that's what's happening. Okay, then I am going to have to zip through this. So this I won't be able to cover in detail. This is also something which you should, again, like I said, this bound is something that you need to learn to love. And this is called the Elias-Fano representation, and it has many uses. And it's really straightforward. If you have the slides, then you can just look through it. But I won't be able to cover this because I need to move on to some other things now. So this Elias-Fano, Elias-Fano. I really feel bad about this because Fano is my academic great-great-great-great-great-great-grandfather or something. So I shouldn't say this, but sorry, great-great-grandfather. I'm skipping. So the thing about this is that it's really very nice. So let me just tell you what it does before I just skip the details. But it basically, what it does is it takes this bit string. This bit string is sparse, so it's got m ones in it, and then it stores it in this bound. Okay, and what it does is it performs select operations in the bit string. Okay, and select operation in the bit string is exactly the same as return me the ith largest element of this set, because a bit string is obviously just a set. And it stores it in some kind of compressed way. So if you look at it a little bit more closely, you think of, there are two ways of representing a set. One is just as a bit vector, which is the characteristic vector of the set. And another one is to actually write down all the elements of the set. And this one just provides a smooth trade-off in between. Yeah? So it's
bit string is too small.
Yeah.
Does this pay off or not?
It depends. Again, like I said, so this can be used. This is actually just a way of compressing this bit string. So depending on the application, it can still be useful. But we are assuming that these bit strings are. So this is just a compression method as well. So I can easily see that it can be used. You can take some small blocks, compress it using this, and it helps. It's fast to decode as well. So it's potentially useful. Yeah. So what can we do with Elias-Fano? For example, you take an inverted index. So what's an inverted index? You've got a keyword and positions where it appears. And the positions where it appears can basically be considered as a set or a set of increasing numbers. Now what you can do is you can store this in Elias-Fano. And whereas most of the time when you see how to store an inverted index, you say, well, here are all the numbers in the inverted index, take the difference between them and encode the difference using some funny code like variable length code of some kind or the other. This is very nice and it gives you pretty good compression, but you can't randomly access, right? So if, for example, if I want to do an intersection between two inverted lists by doing binary search in one of them, so this is not going to work. So random access can be quite useful. Adjacency lists, so for example, you might want to directly access the ith neighbor of a vertex, for example, also can be done using this. So this is nice. It gives you compression and also random access. It matches the information theoretic lower bound for random sets. Okay, but if you've got sets like this, so again, here's a set where this is the universe is basically 1 to n, and you have the first m minus 1 numbers in the set, and then you have the last one. So clearly this isn't supposed, this is a very compressible set. This can easily be somehow, you can think of very many different ways of encoding this in a much less smaller way than the bound which was up here. Yeah. So there's a very nice paper. It won the best paper award in SIG IR, which basically says that you take your big bit vector, you find an optimal way of partitioning this bit vector. So you take this part, this part, this part, and you apply Elias-Fano individually to each one of them. And this basically is as good as the best way of compressing inverted indices, and it gives you constant time random access, which is really nice. Yeah. So Elias-Fano is nice. Next I wanted to, so that's basically all I want to say about, and then the thing is when we come to these applications, then I'll be using these data structures, so we're telling you how to use all of them. So we might have to come back to these slides to remind you what they do, but for now just, yeah. Okay, so next is an n-node binary tree, and I think, if I'm not mistaken, this was actually used in the, I made this slide, of course, before, but I think this was actually used in the SURF paper yesterday. So this is so like I said, the information theoretic lower bound is basically 2n bits. How do you encode a binary tree in 2n bits and still do navigation operations? That's the main point. Not just encode, but you should be able to navigate, which is you go to it from a node to its left child, to its right child, to its parent. It's a very straightforward encoding, and this is basically goes back to Jacobson's thing. What you do is you just scan these. So here this is sort of my binary tree. These nodes out here are not necessarily part of the binary tree, the square nodes. These are the external nodes. So what I do is if my binary tree comes without these external nodes, I actually put them in there. Okay, so I put all of them in there. And then what happens is I just scan this in level order. Every time I see an internal node, one which has at least one child, I output a 1. If I see an external node, then I output a 0. I spend a little bit of time, you'll see that this is a unique encoding of the thing. And if the binary tree has n internal nodes, so these are the n of the red one, the circular ones over here, then it has n plus 1 of the external nodes. So this entire encoding has taken 2n plus 1 bits, which is only a very small additive factor away from the lower bound. And it's also not very hard to see that if I want to do like navigation operations, then I can just sort of, it's just basically a rank and a select. So it's almost exactly the same reasoning as you would if you've got an array and you want to store a heap. Then the children of the node at position I are at 2i and 2i plus 1. So that's basically what's happening over there with a slightly not very balanced structure, but it's basically the same reasoning. So just a rank operation will allow you to go to the right child, and another rank operation allows you to go to the left child, and to go to the parent, you just do a select operation. I won't go into the details of this, just these formulas are fairly obvious. You can just take a look at them and convince yourself that it works. So, so therefore, if you can do rank and select, so you take your bit string with 2n bits, add little o of n bits to it, now you get a binary tree where you can do all these navigations in constant time. So you've got lots of tree representation. So this one, I mean, I could give us a 2-day tutorial on tree representations alone. There's lots of papers. I just want to, so here, for example, I want to tell you about how some of the strengths, these amazing strengths. I'm sorry you can't read all of these. It's a slightly smaller. But here's a paper. This paper's called Fully Functional Succinct Trees. The word is fully functional. So this is for something called ordinal trees. So what's an ordinal tree? Just think of, if you know XML documents, think of what the tree structure of an XML document looks like. It's a rooted tree. The degree can be arbitrary, but the order of the children matters. Lower bound for that is also 2n bits. So here's the representation that in 2n plus little o of n bits supports all these operations. So this operation over here is you can access, you can index the nodes in pre-order or post-order. You can go to the first child. I can randomly access the ith child, regardless of the degree of the node. I can find the level ancestor. So the tree may not be balanced. The tree may be really long. I come over here and I can find my level ancestor, means I can randomly access the path up. No problem. I take 2 nodes, not a balanced tree, find the lowest common ancestor. All of this in 2n plus little o of n bits. Okay, if you think of a normal representation that does all of this, it's you know, you have to have data structure after data structure. It'll be order of n space, but with a huge constant. And the really nice thing about it is that what's happened is by adding all these functionalities, you just have sort of a tree representation of 2n bits, and then lots of little o of n bit additional indices that support these operations. So there's a constant over here, but the constant is hiding in here, which is kind of nice. Yeah. So this is one of the strengths of succinct data structures, so that you can a single representation can do a huge number of functionality, huge amounts of different kinds of functionality. But so this is the good functionality at low space cost, but it's got very strange limitations on its functionality. So one of the operations over here is called pre-select, post-select, which means that get the ith node in pre-order, get the ith node in post-order. You can randomly access these guys. Okay, so that's nice. So now if I say what I would like to index them in BFS order. So get me the ith node in BFS order. This is not supported by this. And the question is, I would like to also support it in BFS order. I'm sorry, I can't do that. I mean, as far as I know, it's basically impossible. There's one of the things, it's on my list of things that I try to convince my community members to do, is to prove a lower bound that this is not possible, but they, so far, nobody's done this yet. But I believe it's impossible. So now if you say I want an application which would like to access, index a node in BFS order and in pre-order, you say, okay, well, there's no problem. There's other tree representations that you can index in BFS order. So that one, the binary tree representation basically went through nodes in level order, and if you do the same with ordinal trees, you can index in BFS order, no problem. So it's okay, here's one which indexes in pre-order, here's one that indexes in BFS order, we're set. The problem is that most of the time, you would like to make sure that you're traversing the same node in both trees, which means now you need a mapping from a BFS ID to a pre-order ID. And this mapping is going to take n log n bits to store. So it's basically, it's not going to work. So this is going to be quite challenging. I think there's a way to do it, but it's incredibly complicated. So it's just pointing out some of the limitations of these things. So you see this list of operations and you think, let's just add this operation, should be simple. It may not be simple. Yeah. So keep that in mind. Yeah. Okay, okay, let me tell you one more. So I think what I'll try to do is I just, this one is really very nice as well, called a wavelet tree. Okay, I'll have to talk about this for a second, so let me talk about this. So we talked about rank and select on individual, on a bit string. So we said rank and select, if I've got a bit string, 0 and 1, rank means how many ones, rank 1 means how many ones are there up to a position, rank 0 means how many zeros are there up to a position. So now if you have a sequence of symbols from a larger alphabet, not just 0 and 1, well, it's easy to generalize the notion of rank and select. Yeah. So rank Ci basically means the number of Cs in the first I positions of this sequence, and select is exactly the same. And then you've got this operation called access, for example. So what we want to do is, so this very nice data structure called the wavelet tree does this in order of log of sigma time. So it's in one sense, a generalization of a straightforward bit vector. The space usage is n log sigma. This is the information theoretic lower bound for this, plus a lower order term. And how does it work? It's pretty straightforward, actually. So unfortunately, again, this example is a little bit small for the people at the back of the room. But here's my sequence, and this sequence 4, 3, 0, 5, and so on and so forth. So what I do is I just take the most significant bit. So the most significant, so we are assuming that these are all 3-bit values for now. So the most significant bit of 4 is 1, so I write down 1. The most significant bit of 3 is 0, so I write down 0, and so on and so forth. So now what I do is I now got a bit string, and the bit string just tells me what the most significant bit of each symbol is. And now I use rank and select to basically take all the 0 first bit symbols and make them into a subsequence, a contiguous subsequence. So all these guys are mapped using rank and select operations down to another bit vector. And this now contains all the numbers with whose initial leading or first order bit was 0. And this contains all the numbers which had a leading bit of 1. But of course, you don't have to store the leading bit because you know they're all 0 and 1, so you just remove them. Now you actually have slightly shorter bit strings. And you continue like this, and you get a tree of height order log sigma, and it's very easy to see how to do these rank operations by just walking down this tree. So it's pretty straightforward. This is a really nice data structure, very useful. So you can sort of, the alphabet doesn't have to be particularly small. So for example, if I've got a permutation, so I've got a permutation over 1 to n, then this can be viewed as a, so this thing on the left over here is a permutation over 1 to n, and this can be viewed as a 2D point set. So this basically is the value of this is basically where the first element of the permutation is mapped, this is where the second element is mapped, and so on and so forth. And what this range tree effectively does is to sort of take the ones which are mapped to the second half of 1 to n, and using rank and select, it then basically reduces to an n by 2 by n by 2 permutation. And therefore now, with one rank and select, you go from this particular diagram over here to this diagram over here. And those of you who've studied range trees, that's basically what range trees do. And the main thing about this as compared to a range tree is that whereas a range tree would use pointers to say that, for example, that this item is the same as this item, that's basically how a range tree would work. It would have an array of pointers. This one basically uses a bit vector. And an array of pointers is n log n bits. A bit vector is n bits. So therefore, what this whole thing does is basically it uses n log n bits instead of n log n words. And therefore, it uses only order of n words of space. So this is quite nice. Yeah. So that's the one view of the wavelet tree. And using the wavelet tree, you can now do all sorts of because it's a range tree. So whatever you can do with a range tree, you can basically do with a wavelet tree. You do range queries. There's a whole bunch of stuff. You can. Okay, we'll talk about this a little bit later. But basically, any kind of orthogonal range search you can basically do in using a wavelet tree. Okay, and this is it's a very fundamental data structure, and it's used very well supported by libraries. Okay. I was going to talk a little bit about this data structure over here called the wavelet trie, which was presented at PODS a few years ago, but I won't have time, and it's not that relevant for the rest of the things, so I'm going to skip over the wavelet trie. It's just a generalization of the wavelet trees to sequences of variable length strings. It's a very nice paper, at least it's useful to see what it does, because it's again one of these little magic data structures. Okay, so the final data structure that I want to talk about is again magic data structure. This is a whole, again, entire sub-area of succinct data structures called compressed text indexing. I mean, I have to say that every year there are 20, 30 papers on this subject. I cannot say I keep track of all of them. They all, but there's all sorts of little variations, trade-offs that you can put in, and so on and so forth. But this is a very fundamental task that it does. So I've got a sequence, and here to sort of be consistent with the appropriate subcommunity of algorithms, this sequence is called T, and T stands for text. And it's a symbol of n alphabets from it's a sequence of n symbols from an alphabet of size sigma. And the space usage is supposed to be this. That's the information theoretic lower bound. And the operation is very straightforward. Given a pattern P, I just want to count the number of times that P occurs exactly. So I don't want to, the pattern matches, I've got the big text, I pre-process this text, then I give you a pattern. It's how many times does this pattern appear in the text? Sorry, the pattern is a string? A pattern is also a string, yeah. Yeah, sorry, a pattern is also at the moment very good. It's a string, it's not a regular expression, it's just a string. Yeah. Yeah. So the standard data structure we talked about was the suffix tree, which answers this query in order of p time, no problem for it. But the suffix tree in practice is 10 to 30 times larger than the text, so we don't want to use it for relatively large data sets. So a number of succinct data structures have been developed. We'll focus on something called the FM index. FM stands for Faragina and Manzini, who are the inventors of this. They didn't name it FM index, everybody else named it FM index. And there's a notable alternative which is called the compressed suffix array, and these two basically came out simultaneously. Very similar functionality. I think it's much easier for me to talk about the FM index because the notation is just, there's no notation. That's really nice about it. So FM index, yeah. FM index is again a little piece of magic, so I like it. And how many times? How many times? If it occurs 200 times, then it answers 200. Yeah. And yeah, if you want to ask what happens apart from that, that's on the slide after this. Yeah. It's as usual. It's this magic data structure which has, it's a magic bullet, but with all sorts of strange weaknesses. It's a magic bullet that works against only one kind of animal and is useless against other kind of animals. Not useless. It just has limitations. Okay, so good. So the FM index is based on something called the Burrows-Wheeler transform, and if those of you who studied compression would have seen this. If you haven't, it's a very nice thing to take a look at. It's a lovely compression algorithm. So and this is sort of the. I'm very happy that I'm in America because every single example for the Burrows-Wheeler transform is always Mississippi. So Mississippi is the standard one. So I'm happy to be giving this number. So what do we do for the Burrows-Wheeler transform? It's very straightforward. I take my text, which is Mississippi, and I take all rotations of my text. So right. So this is Mississippi, and these are all the other rotations of Mississippi. Okay. And what I do is I put these rotations in lexicograph. Yeah? Rotation is just so I took here's Mississippi, so I took the I and I put it here and so on. Yeah, so that's it. Yeah, nothing. And now what I've done is I've taken all the rotations of the string and I put them in lexicographic order. So this one is this rotation comes before this rotation, and this rotation comes after that, and so on and so forth. Okay. So now the output over here of the Burrows-Wheeler transform is actually very simple. Burrows is just this last column of this matrix. Okay. A couple of observations about this last column is that it contains obviously all the characters in the input in their appropriate multiplicities. Yeah. And so from the last column you can figure out the first column because the first column is exactly those characters in those multiplicities but in sorted order. So you write down the first column. The first column and the last column are important. A couple of other observations over here is that if I take an element in the first column, then this P over here is followed immediately by this I over here. So whatever is in the last column, the corresponding thing in the first column is the character that appears in it in the original text. Yeah. And now you can sort of see that it might, but it's not that simple. Just a very simple thing. One further little observation that you have to make is because of the lexicographic sorting, there is a very straightforward relationship between the first column and the last column. So what I've done now is I've put the first column to the right so that you know that the P is followed by the I in the text, and here's the last column and here's the first column. And it turns out, it's not very hard to prove at all, that this P over here has got to be identical to this P over here. This S has to be this S. It can't be any. There are 4 S's over here, but it's got to be this S, and so on and so forth. So they basically, the order in which a particular symbol appears among all the equal symbols, the order in which they appear in the left column, the last column is exactly the same as the order in which they appear in the first column. And now this mapping is now obvious. So I can do this with rank and select operations. So if I do, now what I do is clearly, I mean, if I have, once I do the Burrows-Wheeler transform, this is the critical one. This one can be derived very straightforwardly and can also be stored in very little space, because it's just, you say how many A's there are, how many B's there are, and that's basically a representation of this left column. So the left column is completely unimportant and takes no space at all. The right column is what you basically store, and the mapping between these two is done with
Space measure, no space at all. I've never heard such a thing.
well, sigma log n, you know, I mean, yeah, okay, fine, whatever. Thank you, yes, no space at all, yes. Negligible space, forget about it, you know, hide it, you know.
Big O, little o, tiny o.
Tiny O. That's a very very good. Yes, we have to. This is new contribution to the asymptotic analysis of algorithm. I really have to think about this. This is very nice. Yeah. No, because actually, to be honest, I see some point in this, because there's big O and there's little o. Where little o sometimes is very close to the big O, and then there's tiny o, which means it really doesn't matter, and this really doesn't matter. Yeah. So. Okay, what's really nice about this is that I can now do some amazing stuff. I can now use this data structure just for counting. Okay, and the main thing is called something called backward search, and I'll just try to illustrate this very briefly. So I want to see how many times this pattern SIS occurs. And what I'm going to do is I'm going to see how many times S occurs. Then I'm going to see how many times IS occurs. Okay. Then I'm going to figure out how many times SIS occurs. So let's just, in fact, let's just do occurrences of IS, because that's a little bit more interesting. So how many times does S occur? 4 times. Okay. How many times does IS occur? Well, here's my L. This is the thing. This is the difficult string which I actually store, and each of these S's is preceded by the corresponding character over here. So what I do is I take this particular, just these 4 positions in the L column and count how many I's there are inside there. That's how many IS's I have. And I can do this counting by doing 2 rank operations. I do a rank over here, and then have it. And then I do a select, and then map these guys over here, and then I get these 2 I's over here, and then I can see that there's only 1 occurrence of SIS. Okay, so this is quite nice. So this is really nice. I can do counting now. It takes order of p times log of sigma time. Why does it take log of sigma time? Because these rank and select operations on these thing takes log of sigma time. Now what's really even amazing is that this thing over here is actually extremely compressible. It may not look like this, but actually in practice it is extremely compressible. In fact, every like bzip, for example, basically just compresses this. So if I store this in a slightly compressed format and still support rank and select, which is not that hard, then I've compressed the entire text to within its kth order entropy. And what I get is I get this full text index, which means I can, it's not like an inverted index. Inverted index tells you where certain words occur. This tells you where any pattern occurs. And so for example, in DNA sequence where there are no obvious words, then this will allow you to search for any subpattern. And basically this plus rank and select is the index, and therefore the text is indexing itself. So it's called a self-indexing text. It occupies 20 to 30% of the text size. It's competitive in size with inverted indices, but much more powerful and very fast. Magic. Okay. Now you say, okay, here's my thing. Okay, it's all very nice, but I just want to read my text. You can find patterns in the text, but I would like to read my text. You can't read the text. Okay, so the only way to read the text is by storing a permutation and then sparsifying it. To read a single character of the text takes log n times log squared sigma time. It's not nice. Okay.
Does it make sense?
Well, you might. I mean, you might find a. Okay, so then okay, that's okay. Fine. You may not want to read the text, but I would at least like to find the positions of the matches. I've told you have 200 matches. I would like to know where the matches are. And now to find a position, you have to find where it is in the original text, and it's all this. So it's just so very simple. Additional things just don't happen. But the thing that works very well works like magic. Yeah. So just keep this in mind. Always succinct data structures. If you see a succinct data structure for something and you want something plus X, think twice. It may not be possible, yeah, or it may require a lot of extra work, or not, or a lot of extra space, or it might be a lot slower, or something like that. Yeah. Okay. Okay. So that's basically the end of the FM index, and I would now like to talk to you about this next thing, which is again another obstacle to the use of succinct data structures. It's called dynamization. Everything that I've told you says I have a bit string and I can pre-process this bit string, I can do this, I can do that, and after this pre-processing can answer all these queries very quickly. All these queries, none of them are there were no modifying queries, so counting, doing prefix sums, navigating a tree, none of these are modifications. And dynamization is something where succinct data structures struggle a little bit. Okay, so for example, you got a bit vector. So here's a bit vector, and I say, well, not only rank and select, but I would like to flip a bit. If you remember how it worked previously, you have this big bit vector, then you take some positions, and you store the sums up to that position, and now I flip a bit in the middle of the bit vector, and lots of sums change. Yeah, so there's a lot of things that have changed. And this is not just me being stupid. There's a lower bound which says that if you want to support rank in constant time, then updates must take like square root of n time, or n to the 1/3 time, slow time. Okay, so it's quite slow. What's quite easy is if you want just log n time for all operations, including rank. But that's the problem, is that if you want relatively fast updates like log n time, the query time also becomes log n, which is not very attractive. Okay, and this is true for many dynamic succinct data. You'll see quite a few times the static one takes constant time, and the dynamic one takes log n time, or log divided by log log, or something like that. Not very different. But one thing that is very nice is that quite a few papers have shown that so the thing about this flip, so just think of this, the flip is a random access update, because I say flip of I means I've got this entire bit string. I can jump anywhere there and flip the bit. This is not easy. But if I say actually, I'm actually right now, all my modifications are in the middle of the bit vector, and I'm going to change a bit over here, then I might move, I might have this notion like a finger, right? I have the finger in the middle of the bit vector, I can change that bit. I'm allowed to move the finger a little bit, change that bit, move it there a little bit, again change that bit. That becomes a lot easier. For example, if you take this, if I took the naive data structure that I told you about, the data structure I told you about, static data structure I told you for rank, and think about appending a bit. So appending is quite harmless, right? Because all the previous prefix sums haven't changed, and then it's quite, you can see this. Now if I have a bit vector where all the action is happening around a finger, you can sort of think of doing this. It's a very standard Turing machine trick where you have updating in the middle of a tape is basically done by having stacks. Basically a simulation of this by 2 stacks or something like that, right? So you can do something like that, and you can do, so many of these things are updates for constant time updates, constant time queries are possible if they all have locality, which could be quite true in many practical applications. And the lower bound doesn't apply to problems like hashing, so dictionaries have no lower bound, and we have succinct dynamic dictionaries, and using this we can implement dynamic tries, and we can implement things like variable length arrays. So you've got a big array, some entries take 2 bits, some take 4 bits, some take a lot more, and you want to store this in the minimum possible space, but I'm allowed to change them. So what used to be a 4-bit value now is a 32-bit value, and so on and so forth. That can be done using this. This was a paper by us in Alenex. And there's also this very nice stuff over here, which I think I'm going to have to skip because I'm short of time over here. So, okay, good. So this is a real problem, and in the conclusion slide, I'll also tell you that the other thing that we absolutely do not consider, which coming and talking to Sigmod people is going to make me look like an idiot, is we absolutely do not look at concurrent we don't look at updates, okay, not that much. So concurrent updates, acid properties, no, it's just persistence, no, we don't think about these things. So if you guys come and tell us this is really important, then it'll force us to think about these things. So please do come and tell us that.
Very important.
It's very important. There we go. Thank you. Okay, great. So I'm again a little bit short of time. So I'll tell you that there are libraries. This is the library of choice, SDSL Lite. It's one of the better ones. It's not super fast, but using SDSL Lite, you can. So I'm going to give you some applications at the end of this, okay? Some of these applications are things that now with SDSL Lite, you can get one of your undergraduate or master's students to do in a couple of months. It's very straightforward. So libraries are nice. Not dynamic. There's no dynamic over here. So dynamic just means do the whole data structure from scratch. Okay, it's nice. It does all sorts of stuff. Okay, so because I'm short of time, if you don't mind, I'll just move straight on to my discussion of the applications. Like I said, none of these applications is a fully fledged database system. But yeah, just want to. Okay, so the first application is something that drew me into this was working on XML representations. What's our data? Data is XML files. I'm not going to talk about information theoretic lower bound over here. Operations, there are lots of operations. So DOM has an API, and XPath has an API, XQuery has an API. So the set of operations is very well defined over here. What's an XML document look like? Well, it's basically looks like this. It's a tree, and there's some textual data, and the nodes have tags, so they have labels, and you've got the tree structure. So you've got attributes, but let's not worry about attributes for now. Yeah. So what can we do with this? And the problem is that if you take a look at implementation like Xerces, then if you have a disk file size of a certain 1 gig, then your DOM tree is 15 gig, and that's not very nice. That's called XML bloat. So how do you do this? Well, it's pretty straightforward. So what you do is you just, our first paper was really, there was a fair amount of optimization that went into it, but the eventual application, like I said, was really straightforward. So I told you that tree can be represented succinctly, okay? So straight plugin of SDS. So we used a couple of bit vectors for various things. We talked about an ordinal tree representation. Well, what's an ordinal tree? Well, that's an ordinal tree. So take a succinct version of that, put it in. Then we used alias. So basically, the text was all stored out in an array, and alias fano was used to say this particular string begins here, this begins here, this begins here. It's again a sequence of increasing numbers. Plug in. That was it. And then, of course, a little bit of implementation. And we basically got with the main difficulty, of course, was that at the time the libraries were not there, so we have to implement them, engineer them, and all this kind of stuff. And that's where the work was. And we got some reasonable results. If, even if the XML file is small, then we're only 2 to 3 times slower. For larger files where the DOM was sort of barely fitting into memory, then it was really almost as fast, and we got 10 times memory reduction. Yeah. And then there was a further paper by Arroyuelo et al. And a bunch of people, ICDE 10. So again, they basically wanted to do this, but they wanted to support core XPath. And again, I think now you look at it, and all these data structures are here. It was basically a tree, okay? Then they took the text, and because XPath has queries that allow you to search the text nodes of a thing, so they put the text in the FM index, which told you about. And then for tags, they used alias fano. So this is one of the nice uses of alias fano. Alias fano 1, lots of alias fano, one alias fano for each particular tag. And because of the properties of alias fano, that turns out to be information theoretically optimal as well. And so they got this. They got good space savings, and it was quite competitive. But it's again still at proof of concept level, I think. Yeah. So then there were a couple of other very nice. This is a really nice paper, in my opinion. If anybody is at all still interested in XML data, This is a really nice thing. So we talked about the FM index, which was this wonderful data structure for counting queries and so on. How do you generalize this to trees? So you've got trees, and now what you want to do is you want to find all the nodes which are labeled by a particular subpath, and this can be done in it's a really nice paper, and I think it's worth looking at. And then there were other things like tree compression using something called top trees, which is a kind of grammar compression. And then there's people like Sebastian Manath and Marcos Lorai. They basically do this. They have grammars, lots of grammars, and lots of and very, very clever algorithms for actually compressing trees using these grammars and for navigating these compressed. I'm not such a huge sort of fan of this work because the theoretical bounds aren't always there, and also because in XML documents you can grammar compress the tree, but then all the other stuff remains. But that's fine. It's really nice work. I'm not denying the quality of the work here. So that's succinct XML representations, and like I said, you can knock up the first two months max. Okay, from beginning to end nowadays. Yeah. Then there's stuff about graph similarity search. I won't sort of, again, a little bit sort of short of time, so I won't talk too much about this, but basically they used the wavelet tree, and so their application was that they have a database of chemical compounds, and the chemical compounds are labeled with a sequence of attributes. Then what happens, you've got another chemical compound, you have to do a similarity search. So they basically use the standard techniques from IR for finding similar documents. The only thing which was slightly different is that the query is quite large. So typically in information retrieval, when you ask a query, then you have a small handful of keywords. Here you've got a completely new protein which has maybe 30 to 40 keywords or attributes. So it's slightly different, and they used this. And this is a paper in SDM 2011, and they got some fairly good results. And again, nowadays with SDSL, this is just a plug and play. You can just implement this. This will take 2 days to implement. Yeah. And then there was a paper in KDD 13, which basically you got the feature vector as before, but then each particular so in addition to for each particular protein which is described by a feature vector, you also have a numeric thing which tells you something about its functionality. So in addition to finding similar things, you also must find a similar in terms of the keywords, but also this functionality thing must lie within a range. And basically what they did was they took their previous work on similarity search and added to that a wavelet tree for putting on the orthogonal thing. And then again, this was very nice, and it was very scalable, and it gave very nice results, and that was, like I said, a KDD paper. Yeah. And then this is sort of stuff which is not, I would say that it's not, this is slightly, this is just an example over here, and this is not as well developed as the other things, but this is for like trajectory data. And what's our data? Our data is a collection of trajectories, and this is what's called a mapped trajectory or network constrained trajectory. So you've got the trajectory data, you've got the GPS coordinates, and then you do a mapping, and you've got a map over here. This map has a slight error. This is showing a directed graph. There are little arrows over here. Ignore the arrows. These are not one-way streets. These are two-way streets. And then what happens is that each trajectory then basically then tells you what road segments you took. So for example, this is FEBA. So this is a trajectory that goes like this. And these things over here, these little superscripts are basically timestamps. Okay, so this is a very standard, relatively standard way of modeling trajectory data. And the query that was sort of proposed in this paper in GIS 14 was something called an exact path query. So you find all the trajectories that contain, so you give a query sequence Q of symbols, which basically represents a potential subpath over here in this network of roads, as it were, and you have to find all the trajectories that contain this as a substring. but you also want like a time constraint, right? So what you want is you want to see how many cars took this particular segment of the road at rush hour. So rush hour is sort of then gives you a time constraint. So that's basically it. So for example, in this particular query, so for example, the query here, we basically we want to ensure that if a match is found in a particular trajectory, then the very first point in the trajectory that matches must fall inside my time interval. So if you look for BA, so BA appears over here, and it appears over here. But if my time constraint is 5, 7, then this B is a 4, so that falls outside. So we just return T2 as the only trajectory that matches. So how do we do this? It's pretty straightforward. Again, so basically all you do is you just create this big trajectory string, concatenate all the trajectories. Standard trick is to put in a little extra symbols to sort of say that basically separate the trajectories. Okay. Then what do? You create an FM index. Okay. And then there's this little stuff over here, which this is the Burrows-Wheeler transform, and in the order of the Burrows-Wheeler transform, you have to associate these particular symbols with an appropriate timestamp. I won't have time to explain exactly how you do this. You actually need to understand the exact working of it, but it's not difficult. I'm happy to explain this to anybody who wants to ask me offline. So the query becomes very straightforward. So when I take a query such as BA, so that was my query example query over there, and then I explain to you how to do a search in the FM index. The search in the FM index basically returns an interval of the Burrows-Wheeler transform, for example, CE. So if the Burrows-Wheeler transform, remember, is the rotations of, it's basically the lexicographically sorted, think of a lexicographically sorted matrix of all rotations. These are the last characters of those rotations, and the first characters of the rotations are basically going to be the patterns that you match. So they're obviously going to be adjacent to each other. So all the positions so these are all the characters that sort of appear just before the match, and these characters over here are going to be consecutive. So you get an interval. So when I do a search in the Burrows-Wheeler transform for a particular string, then I get an interval of the Burrows-Wheeler transform. So I've got an interval over here, and I've got these points over here, which are the times, and now I just have to put a orthogonal range restriction over here, and that's done. And for that, I just use a wavelet tree. So combination of this and these queries are solved as well. Okay. So one of the things over here, so this FM index is basically just a succinct version of the suffix tree. And suffix tree was considered by these authors, but they said, well, it uses too much memory. Well, FM index doesn't use too much memory, and it's also said that that they would like to support updates, and FM index doesn't support really updates, but the kind of updates which are required from trajectory. So what happens in a trajectory database? It's not that you go and say, well, that was the trajectory, I'm going to change it. Now I'm going to get a new trajectory, add it. So it's just adding things to the back, and that is still not supported, but not as badly not supported as arbitrary. I mean, in the sense it can be done. It's almost practical to do this. So it's maybe, so both these reasons were perhaps not reasonable anymore. Okay, so that was my next application, and in the last 2 minutes, I will try to conclude and leave a couple of minutes for questions. So what's the conclusion? So conclusion is, of course, that I hope that use of succinct data structures can allow scalable storage and querying of big data in memory. And the hope is that if you've got a machine with like a terabyte of memory, then you can take really large data sets and store them in memory and query them. So that's the potential over there. The difficulty is that succinct data structures have to be chosen and used appropriately. So when you see a succinct data structure, be very clear what it does, because the chances that it does something related to what you wanted but not quite the same, there's a chance that it actually won't do that. So you've got to be a bit careful over there. And there's a lot of room for application-specific tweaks and heuristics. So this, for example, the best paper this was a perfect example of that. They looked at exactly what they wanted to do, and they took the standard succinct data structure, they modified it, and they got perfect performance for that. So this kind of work is always there, but for that, I think to some extent, you need to know your succinct data structures. So that's a slight disadvantage over there. And like I said, many of the basic theoretical foundations have, so there's in the theory, very basic theory of succinct data structures, most of the basic problems have been studied, so that's not an issue anymore. And not only are the theoretical results there, many of these things have been built into software and libraries, so they're much, I can't think of, this is the time when it's really easy to use. You can knock up these applications fairly fast if you want to use them. But of course, it's only for static applications. So when it comes to dynamization, none of these libraries are going to do very much. Concurrent access, asset properties, nothing really. So again, these are things where, so basically my suggestion to you is if you're interested in this kind of stuff, we have in-memory databases which are requiring lots of memory, then just either read up about succinct data structures or find somebody who works on succinct data structures and talk to them and see where you can get, because it's potential for some new theoretically interesting work, and certainly obviously from the performance of perspective from the database side of things as well. Okay, so I stop now, leaving barely 1 minute for questions, but yeah.
Thank you, Rajeev. We have time for questions. Can I ask you to step up to the microphone, whoever has questions, so that we get this on camera?
So, if we care about performance, seems to me is we can have today memory with probably up to terabyte, but the idea is that you have the size of a word is log n.
Yeah.
So the size of a word is 64 bits.
Yeah.
64 bits. I mean, this is it. It's pretty much built in, 64 bits. Maybe you can, depending on the instruction set, you can talk about you can have access to 32 bits, but you don't have access to log n. The second thing, if you really care about performance, you cannot ignore cache effects. Cache effects are incredibly significant.
So
If we ignore them, it means we are not going to get good performance without paying attention to cache.
yes. So this is the difficulty, is that there are lots of papers on theory of succinct data structures, and there are equally large numbers of papers on implementation of them, where we all say always, for example, like I said, so there is a very good case to be made that memory access is not constant time but log n time. And that's very simple, very straightforward, because if you have a very large data set, then most of the time, unless you use very large pages, you're going to have TLB misses. And a TLB, if you have a TLB miss, then there's a search tree that you have to go through, so it takes log n time, and there's very well documented. You can just do this text. You take a large array, and you do random accesses to this large array, and you get a log n time graph. Okay, so therefore, I mean, so the model is very much in question, and this is the algorithms community has been living this lie for the last 40 years. They work on a particular model. They know the model is not very good. So there are all these people who do things called algorithm engineering, which say that, look, if I actually implemented what was in the paper, then it's going to be rubbish, so I'm going to do something completely different. And we live. That's it. What can we say? Every point that you made is absolutely valid. Yeah. Okay.
Hello. So is there any way you can go below the information theoretical lower bound by using, for example, properties of the specific data that you have?
Right. Yes. So, like I said, the information theoretical lower bound is, for example, you have to be very careful about what the information theoretical lower bound says. So, for example, you say binary tree has 2n bits, but if you know your tree is balanced, the information theoretical lower bound for that would actually be different. And so a balanced binary tree, I believe, can probably be stored in less space than this information theoretical lower bound. And again, like I said, the information theoretical lower bound doesn't. So if your application says that so you've got a basic class of data, the application says that there are some constraints on this, then the information theoretic lower bound in one sense changes. So you can go below the generic information theoretic lower bound. Yeah.
But then you have to specifically kind of other techniques to construct your data structure so that it matches
this is the thing is that I don't know your problem, okay? I don't know your constraints. The answer to your question is yes, okay? And it's because of the very simple thing. The very simple thing is that the last step in the basic step in every succinct data structure is I do table lookup. Okay, so I do table lookup. So what you do is you say, well, I have these very small instances of my problem. Of course, this assumes that your whatever constraints you have at the top level, when you decompose it, they apply to the smaller parts. There's the one assumption over there. But if they do, then you've got these small pieces. Now, I've got a small piece, for example, a graph with n nodes. Let's say that this graph also is planar. So what I do is I enumerate all planar graphs of n nodes for very small n, and that's my encoding. And this encoding, if there are k such graphs, this table is of size k, and the encoding is log k bits. We achieve the information theoretic lower bound. Yeah. So it's in theory, all this is doable. Yeah.
So, Marty, my other question is, so given that the whole idea of this process is to create lookup tables, so I suppose that is also possible to implement such data structures in secondary memory. So I would like to ask if that's the case, or actually for secondary memory we need to do something else.
So yeah, so but the lookup tables for sure. The assumption in all these things is that the lookup tables fit into main memory. So if you're doing something with, but that would not be a very good assumption. I think if you had, for example, you say I take a page, and I want to operate. Yeah, so I think there would have to be some kind of if you were to do that in secondary memory, then what you would have to do is you would have to break your, and this again is a kind of standard technique that you would use in many succinct data structures, is like I said, you take the big problem, then you break it up into sub-problems. So first you were doing in secondary memory, you break it up into page size pieces. And the page size piece, each one of them you treat like an internal memory thing. Yeah, so that's probably how, yeah.
So I was interested in this problem of finding occurrences of a pattern in a text and counting how many there are.
Yeah.
But if the pattern is something more complicated than a fixed text, like a regular expression,
Yes.
and also if the underlying text can be updated, so in the dynamic context that you mentioned.
Yeah, so again, like I said, there are for each of your questions, there are lots of specific instantiations of your question. So specific instantiations of your questions is you're allowed to delete a character, add a character, modify a character. Then you'll have specific instantiation of what exactly the kind of problem. So for every pair of those, there is a potential open problem, and some of them are solved open problems, and there are theory papers out there. But this is the thing which which makes it a bit difficult, is that there is no. Quite often there is no generic solution.
And is there some kind of survey for a map of which combinations of these problems are open?
Yeah, there might be a survey paper. I don't follow that literature as well as I could, because it's exploding literature. I can't keep up with that's a completely. I work in the data structures community. This is a string matching community, a very active community. I can't keep up with everything that they do, actually. But if you're interested, I can find some references. Yeah.
So you show some techniques to encode succinctly and also do some operations. But what about lower bounds? If I know the minimum that I can encode, but I want to do some weird operations. Do you have techniques to show that you cannot do it? Or is that, open?
No, right. So as you say, the weird operations and so on. So then the I'm not aware of any. Oh, no, it's not completely true. So I think there are some. I have to think about this, but so obviously there are general data structure lower bounds. But general data structure lower bound basically says that, for example, if you use polynomial space, then you can't solve these kinds of queries faster than something or the other. So and these data structure lower bounds quite hard to get. So for every major problem that you want to find a lower bound, then that's usually like a stock paper or something to prove a new lower bound and so on. So these are quite challenging things because the model of computation is very general. It's just any old computer. It's just like a RAM. So you have to make some interesting communication complexity type arguments or something like that. And now what you're saying is that what happens when you come to the actual space. And so there are some papers that, for example, say that they try to prove lower bounds on the redundancy, right? So for example, if you have a bit vector of n bits and then you allow certain extra space, how much extra space do you need to do to support rank in constant time? And there's lower bounds for that. But for your particular question, so what you're basically asking is, are there situations where your weird operation now suddenly takes a lot of space because you want very little space, whereas if you just had like linear space on a normal data structure, then you could do it. And this separation, I don't believe that there is a lot of the techniques just are not good enough to make